Good morning. We're going to continue talking about the NRCS method today. And the homework assignment that goes along with that idea is due on Tuesday. There are a couple of those problems that probably you could already start working on, and some of the things that we cover in class today will tie up the rest of the ideas. Before we get into that, though, since I think we had a little bit of extra time in the lecture that we are going to cover today, I wanted to give you an essay that was written. It's a brief essay, just 2 pages long, back in 2009. And it's kind of an interesting analysis of the financial crisis that was going on at that time. Maybe you remember it, but when you were younger, there was a financial crisis that was precipitated by kind of loose standards in mortgage lending and a lot of kind of machinations that were going on with that, like big banks were giving loans to people who didn't really qualify for those loans or who didn't provide any documentation, and then they were taking those loans and packaging them together and selling them as securities, and it really destabilized the economy. And the stock market went really bad, and a lot of people lost their jobs. In fact, there was a big slowdown in the economy. And the reason I bring it up is you're going to be joining the workforce soon professionally. You know, you're going to be beginning your career, and there have been a lot of studies that show that your lifetime earnings are hugely dependent on the state of the economy when you enter the job market. And if you enter the job market before the economy tanks, you're going to be really just getting in there in the last minute, because right now, since the last financial crisis, we've had a period of growth and stability that's longer than any previous period of growth and stability since the Great Depression. So a lot of people just agree, you know, the economy goes through cycles, and we've been through a long growth cycle, and we're overdue for a contraction. So I hope you get out of here before things get ugly. Because if you don't, then things could be ugly. But even when the economy is doing poorly, sometimes it's easy for us to fixate on the short term and not fully comprehend and appreciate and understand the long-term structural advantages that we have here in the United States. And this essay kind of takes an interesting look at why the United States is naturally prosperous. And before I read it, it's not anything I had ever considered as a source of America's strength. I'd always thought, oh, it's because we had such wise founding fathers, or it's because, you know, blessings from above, or, you know, I don't know. It's just kind of like the rah-rah patriotic rhetoric that you hear on the 4th of July. I mean, but there are physical, measurable, explainable reasons for why the United States is perpetually prosperous, and this goes into it. So I'm going to pause for a moment, give you a chance to read this article, and then we're going to take a few minutes to discuss it. Oh, you need one more? There you go. So according to this essay, what are the 2 factors that almost condemns the United States to, how does it put it here, almost condemns it to, well, anyways, the United States is going to be prosperous because of what 2 primary factors? Transportation and the agricultural regions that overlie each other. So I guess together those are the geographic benefits. So there's a lot of arable land. You know, the Midwest is suitable for farming, and then you've got this network of navigable rivers where, you know, a farmer, if we look at a map, I guess if we go Mississippi, then that, this is a good one. So this is showing the watersheds that contribute to the Mississippi River. And of course, there's also the Missouri River that drains even more of it. But farmers as far north as Minnesota, South Dakota are able to put their agricultural products onto barges, and ship traffic can go down the Mississippi River. And as the article was saying, there are a lot of protected ports in the United States, and that's not always the case. A lot of countries have ports that are really strongly affected by the weather, or they have to spend huge amounts of money to excavate inland so that they can have protected bays. But the United States has some of the best ports in the world just naturally, ports and harbors. And then the other thing that's really important about it is not just that it's flat land and that it's got rivers going through it, but also that the soil characteristics and the weather characteristics make it suitable for crops like wheat, soybeans, corn. There are a lot of places in the world that have rivers, but like in the case of Russia, they're flowing the wrong direction. If we take a quick look at the rivers in Russia. Russia has even more land than the United States, and a lot of it could be potentially useful for agriculture, but the problem is that the Russian rivers flow to the north, and so that means that during the winter months those rivers completely freeze over, and so it's not navigable through the entire year like the United States is. Although in some rare occasions there may be a bit of ice on the Ohio River, it's usually just for a few days. But there's a series, I think 5 or 6 large rivers in Russia, and they all flow to the north, and that makes it so that they have to, if they want to use these middle areas for agriculture, then they have to spend a lot more money putting in rail networks or roads, and so the cost of transportation for either rail or highway traffic is a lot higher than, like on a per ton basis. You can move crops around on barges for very, very little. It's extremely cheap. So it's kind of interesting that it says, like on the back side of the paper, it was saying that when you've got get the cake for free, you can afford some pretty nice icing. And the highway systems that the United States built in the 1950s, it was able to make the interstate highway investments at the same time that most of Europe was just kind of dragging itself out of the recovery from World War II, and a lot of other countries just hadn't gotten enough capital together because they didn't have these same structural advantages. So I'm wondering, are there other things that stood out to you as you were reading this as important factors for America's economic growth? Yeah?
So as an investor, would it be a better choice to put in less amount to your retirement fund until it tanks, then put in the full amount because you're going to get the greatest interval amount?
Yeah, so if you know when it's going to tank, if you can time the market, then absolutely. But everyone always talks about the folly of timing the market. So I mentioned that financial crisis. And this kind of shows cycles, right? Cycle, bust, boom and bust. And this is that financial crisis that this was written in. It was like late 2007, early 2008 that things started looking a little bit shaky. And I first got to Marshall in January 2009, and like everyone was walking around shell-shocked at that time. It looked like banks could fail. I felt really lucky to get a loan for my house because there was a big squeeze on lending. People tightened up. Banks were less likely to loan because the credit market was kind of in trouble. So your question, is it better to buy low? Absolutely. But it's only in retrospect that you know when low is and when high is. Like the people, if we just go to some of the specific numbers here, at the peak of that pre-financial crisis, this is one particular stock index. This is called the S&P 500 index. It's a accumulation of 500 of the largest companies in the United States. And so this index was about $150 a share. And so maybe it looked like it had tanked when it was down to 133. The investors thinking, well, it's down already 10%. That's a huge loss. But then it did get as low as $77 a share. But if you could buy in then and now, it's up in the 300 range approximately, approaching 300, then yeah, that's pretty sweet. But I think speaking from my own personal experience, the least maddening way to invest is just to have the same amount go in every month. Just make it automatic enrollment, put in as much as you can afford to, and then just try not to look at it, because sometimes it'll go up, sometimes it'll go down, and it'll just drive you nuts if you fixate on it. Yeah. So one of the things that stood out to me here is about the lack of competition in the Western Hemisphere. Like if you look up and down, both North America, Central America, South America, there aren't a lot of places that have these same advantages that the United States does. There are a handful of places that are nice agricultural regions, like Chile has good arable land. Brazil and Argentina have emerging agricultural sectors, but they don't have this interconnected network of rivers. Another kind of interesting thing is that geography also allows the United States to not have to keep a standing army that's very large. Imagine how different it would be if we had China on one of our borders, or Russia. I mean, they're so far away that it kind of gives the country a little bit of breathing room, and then as it points out here, it ties up a lot of the capital. It frees up a lot of capital and people from having to work in the army or having to work in government subsidized and organized transportation. Now that can go into the free market, which is a lot inherently more efficient. So it's, we talk a lot this semester about how water is a danger, that we have to get out of here, that we have to treat it as a pollutant or a threat to infrastructure. But this, I think, is a good reminder that water is also a resource. And, we already know that since we drink water and it's used for the production of crops, but just water as a means of transportation, whether it's the rivers or the intercoastal waterways on the East Coast, it really kind of shaped what kind of country America is. America probably wouldn't have been successful as laissez-faire capitalism if it didn't have these same structural advantages. If you travel through Europe, you see, the European countries really have to organize to make it work. They have better rail networks than we do. They have lots of locks and dams, and those are huge investments, and taxes are higher over there because they didn't get their cake for free like we did in this country. So I think you should hold on to this. Maybe I'll throw in a question or two on our final exam related to the ideas in here. It's an article that I've held on to, obviously, for 10 years nearly now. I think it's a good one. But now let's talk about the NRCS method. So last time we took a look at these curve number tables. Remind me what the A through D classifications are related to. A through D across the top. It was soil types. Yeah, so on the spectrum of A through D, one of those soil type, at one side you have soils with a high hydraulic conductivity, and on the other you have soils with a low hydraulic conductivity. Do you remember which is which? D, D is clays, plastic soils, saline soils, where there's going to be a low hydraulic conductivity. And so if you look at these numbers, across one of the rows, so if we just look at lawns that are on clay soils are going to have a curve number of 80. And what that means is that there's going to be more runoff than infiltration. But then at the other end of the spectrum, these Class A soils are the ones that are sandy and have relatively high hydraulic conductivity. And so Class A soils have lower curve numbers. So a lower curve number means there's going to be more storage and therefore less runoff. if we just go back to the Nrcs equation, let's take a quick second look at that. Okay, so here's the Nrcs equation, and a big part of that is the storage. And so storage comes from curve number. And if a curve number is big, then what that means is storage is going to be smaller. And so there would be more precipitation excess. But if the curve number is relatively low, that means that the storage and the lion's share of storage is the infiltration, then there would be less precipitation excess. So now back to these tables. It's a combination of land use and soil type. And when we get into modeling on the computer, we're going to use GIS data to tell us in a certain watershed how much residential area do we have, how much streets and roads do we have, how much cultivated agricultural land do we have. That data is out there. It's published by the federal government. And the same thing, we'll have databases of soil type. So these curve number tables that we were looking at are for typical moisture conditions, just kind of not a particularly dry stretch, not a particularly wet stretch. But we need to sometimes be able to convert from those typical moisture conditions to the other ends of the extremes. So what these baseline tables are for curve numbers in type 2 conditions. And type 2 is just the antecedent moisture group that's in the middle. And so what that means is that during the dormant season, for instance now, when the crops aren't growing, we'd expect that in 5 days, excuse me, the rainfall totals during 5 days would be from 1/2 inch to 1.1 inches. And so right now, it hasn't rained here in Huntington for, I don't know, a few days. I don't remember when the last time it rained. Maybe, was it Saturday? I was out at Bridge Day, and it sprinkled on us a little bit. I don't know what it did here. But probably right now, since it hasn't rained here in Huntington for the last few days, in the last 5 days, our total rainfall is less than 0.5 inches. And so that means that the soil conditions are antecedent moisture condition 1 right now. And so what that means is we'd need to, if we're going to do an NRCS analysis, and if we wanted to know how is the watershed going to behave, we couldn't just use these curve number tables and put it into the NRCS method, because right now the soil is a bit drier than these curve number tables are derived for. So here are the formulas. These are just empirical equations that make some adjustment based on observation in the past, and there's nothing fundamental about them. And you know, the conditions really can be different than is predicted here. And you look, it's a range. And so, you know, for instance, antecedent moisture condition 3 is when there's been over 1.1 inches. So it could be 1.11 or it could be 5 inches. And it's going to treat either of those as the same. And so there's limitations to this, but it's a correction that's better than not making any correction. So just to get a feel for these conversions and to show you how widely it causes the curve numbers to differ, let's take a look at, for residential quarter-acre lot on Class B soil, that normally would have a curve number of 75. So let's just go to the table and make sure that we see how we'd get that. So residential quarter-acre lot, Class B soil. So let's go here. Residential is the land covering, and so that's going to be a mix of some roof area, probably an asphalt driveway, a lawn. And so what they're doing is they're saying typically people have a mix of impervious and pervious surfaces in residential area. And the quarter-acre lot is significant because when someone has a 2-acre lot, they're going to have relatively more yard to roof. You know, that ratio would be more favorable towards the impervious compared to the building. So what you'll notice is that as the lot size increases, the curve number is going lower. And that makes sense to us because it's just a reflection of there being more vegetated space as the lot size gets bigger. But in the example that we're going to do, it says quarter-acre lot, and then Class B soil. So we have the intersection of quarter-acre row, Class B, so curve number 75. Now that's only going to be valid, this 75, is if there is, in the past 5 days, between 0.5 and 1.1 inches of rainfall during the dormant season, or 1.4 to 2.1 in the growing season. But we want to find out, what if there's been no rain in the past 5 days? So in other words, find the curve number under type 1 conditions using this formula. And then what would be the curve number if in July, meaning during the growing season, it had rained 3 inches in the last 5 days? So then that puts us into antecedent moisture condition group 3. So find curve number under condition 1 and curve number under condition 3. And we'll look at the range that that gives us. Okay, so what we see is that if the curve number is a 75 under this middle range moisture conditions, then under the type 1 conditions, which means a little drier than average, then it could be as low as 56. Under the wet conditions, it could be as high as 87. So from 56 to 87. Now let's look at what that means. If we go back to the curve number table, okay, we were starting in this example with a residential land, quarter-acre lots on type B soil. 75 is the middle, but it could go from 56 to 87. So try and find something that's similar to 56. If we go to this table, 56 maybe would be like a third-acre lot on type A soil, which is pretty different conditions. Or if we go down here to the croplands, something in the 50s. All right, forest. So a type B soil for forest land on good condition, meaning like the density of the vegetation. It could transform the effect of a residential area, which has quite a lot of impervious area. It could turn it into something that is entirely vegetated, the hydraulic effect of that, if the soil is going to absorb more than average moisture. But then at the other end of the spectrum, taking it to 87, then that's almost like we had taken this grassy area, and now it's going to have the same absorptive ability as like gravel streets. And gravel streets don't absorb as well as vegetated areas. And so it's a pretty big spectrum. And the other way to see that is if we calculate the storage, the S, based on these curve numbers. And so, for example, with the curve number Cn of 87, then S, where S is 1,000 divided by the curve number minus 10. The storage for 87 is 1.494 inches of storage. And for Cn of 56, then the soil has the potential, the maximum storage potential, of 7.86 inches. Now, remember, that doesn't mean that there has to be this much rainfall before there's any rainfall excess. It's not quite like that, but this represents the maximum storage capacity of the soil. And so that, I think, illustrates the effect even more. So the effect of a curve number change isn't linear, is my point. Where we started at 75, if conditions are really dry, then the soil is going to absorb quite a lot more water than if it's been very wet in the past few days. And so the take-home message that you need to take from this is that if you're doing a hydraulic modeling and you want to account for the worst-case scenarios, it's not just analyzing what the watershed will look like when the area is fully built out. And that's an important part of it. And that's a big part of why here in Huntington we have so much flooding, is that they built a lot of the sewers before they had any idea how populated the city was going to be. A lot of neighborhoods that now contribute runoff weren't accounted for in the sizing of those pipes. And so it is important to think, well, I need to put in this infrastructure to handle the demand that there's going to be a long time in the future. So that's definitely part of it. But then also the range of conditions. And so, looking at the range of maximum precipitation for the storm in question, but then also the antecedent, so the prior storms, because that's going to have a huge effect on how the watershed behaves.
So this storage term,
Mm-hmm.
is that, so for a low curve number, you're going to have a high storage.
Mm-hmm.
Is that infiltration storage?
Most of it, yeah.
Okay.
Mm-hmm.
Not
If you go,
excess storage on.
if we go to the precipitation excess formula, it's mostly infiltration, but because our initial abstraction is based on storage, it's also saying that if it's rained recently, then you're going to need less surface wetting before the water starts to flow overland. So the leaves are already wet. The puddle, like the local depressions may already have some water in them. So just everything, all of the abstractions that have to be satisfied before there's runoff, they're more likely to already be close to satisfied when you've had rainy conditions in the previous 5 days. Yeah, so it's mostly infiltration. And by the way, on the quiz, I tried to be generous on it, but on the description between rainfall and rainfall excess, it's not just infiltration that makes them different. Infiltration is the biggest of the factors that cause them to differ, but then there's also surface wetting, interception, local depression storage, and so those are other abstractions that also account for the difference between the two. Infiltration is the most important, but it's not the only one. So are there other questions about antecedent moisture condition? Okay, now luckily we can just come up with a simple weighted average to find out a composite curve number for a basin. It is that simple in a field where not everything can be just area weighted. The composite curve number can. And what I mean by that is if you have a watershed that has different things in it, like if you have a watershed that has some residential areas, some agricultural areas, maybe a commercial zone and so on, and you want to find the overall curve number for that basin, then all you need to do is just multiply the fraction of the watershed by the curve number in question, and then you can come up with an average CN. And so let's take a crack at that. Come up with a weighted curve number for this watershed, and then let's again go through the process of calculating the storage and then the precipitation excess when we have a defined storm depth of 6 inches. So on this, the first step will be to find the average curve number. And it's not a simple average. We're not just adding them together and dividing by 4. But what you should do instead is, based on this land use percentage, where it says 40%, so just multiply 0.4 times the 83 curve number, and then so on and so forth, add them all together. Okay, so the weighted average for this watershed, the curve number should be 86 when we multiply the percent of the area that has each one of those curve numbers. So 86 is the weighted average, so then the average storage capacity inside the watershed is 1.628 inches. And if we have a 6-inch storm, then that means of the 6 inches, 4.41 is going to be rainfall excess. And that's quite a large storm. You remember I told you about the situation they had in Milwaukee back in the early 90s, cryptosporidium, because it got warm really quickly and all the snow melted? They're having a similar thing right now in Austin, Texas, although it's not related to snowfall. It's just that they had a lot of rain all at once, and the river is extremely turbid. Like the suspended soil particles in the water are so high that they can't get them out at the treatment plant. So they're having to, they issued a boil water advisory down in Austin because they know what happens when there's a lot of turbidity. Then the bacteria get through because like the pathogens can hide inside those little soil particles, and they don't get access to the chlorine to inactivate them. So it's kind of interesting. I saw that in the news the same day that we talked about it on Tuesday, that they're having boil water widespread, and it's going to be a long time too, because it's going to be a while before the river levels go down and the scour subsides. So it's a direct relationship between some storm event and then the treatment processes that are required to make the water potable. So this is probably a big enough stream event. 4.41 inches of rainfall excess is going to be so much that there's going to be a lot of flooding and scour. And so just kind of understanding the consequences of hydrologic events like this, I think, is pretty important. Any questions about this example? Now, in this example that we just worked through, we didn't give any attention to where in the watershed different land areas were. And we can do that, and sometimes it makes a difference. This was just kind of like saying we have these isolated areas where there are certain spots that have a pretty high curve number and certain spots at the relatively low curve number, but we're mixing them all together. Sometimes we need to pay attention to the relative position of pervious and impervious areas in a watershed. So take a moment to consider the figure on the left. What this is saying is that we have a 10-acre watershed, just as an illustration, with two distinct land uses. We've got one land use that is pervious area, so that could be grass or other vegetation. And then we have downstream of that, see from this arrow you can see the direction of water movement towards the outlet. But downstream of the pervious area is some impervious surface, so meaning asphalt, concrete, or it could be buildings with roof area. So in this illustration it's saying, let's just take as an example pavement that has a curve number of 98 down here in the impervious area, and then up top let's assume that it's grass with a curve number of 60. So there is a more sophisticated way of determining the effective curve number than a weighted average, because this pervious surface can, if the positions are reversed, allow for some additional infiltration that can't occur right now. And so what I mean right now is the impervious area is directly connected to the outlet. And the effect of that is different than if it's not directly connected to the outlet. If we'll, in the next slide, look at what if it's reversed. What if the impervious is up top? So in this first example, we could either calculate the weighted average, or we could use this nomograph. And so let's just see if we can figure out how to use this nomograph. We have a total of 30% that's impervious, and it's directly connected to the outlet. So if 3 out of 10 acres total is impervious, then what we can do is we can follow here on the x-axis, we find the 30%, and then we would go up to the line that represents the curve number of the pervious area. And so each one of these curves represents what is the curve number of the part that's pervious, and in our case it's 60. So I'll start here at the 30% connected impervious and go up until I reach the 60 curve, and then over to the left from there intersect the vertical axis, and it's 72. So that's how you do it for if it is the impervious area is connected, because there isn't any special absorptive effect that occurs in this configuration. But now consider if the situation is reversed. Mm-hmm. It's because it's 3 acres of the impervious, and the total, meaning area 1 and area 2 together, is 10. And so it's just 3 out of 10, so 30%. Right. Yep. Did you have a question?
Yeah. Why is it that we use the pervious number when you're you're using a connected impervious area, but why are we using the pervious number?
This is kind of a graphical way of coming up with the area weighted average, similar to what we just did. And so it's assuming, in this table, it's assuming that your impervious area is pretty close to 100 for the curve number. So it needs to know for like the combined overall weighted curve number, it needs to know what is this, this grass. In our case, it's grass. If it's going to come up with a weighted average, it already knows that the impervious part is about 100. And so it's asking, so what's the curve number of the part that isn't pervious? So we have to give it some input of, if we're combining two things together. Let me put it on the whiteboard. I think that'll probably eliminate any uncertainty. So we've got the weighted average curve number is going to be the combined effect of the pervious and impervious. And each one of these, the pervious is, we need to know the area times curve number of the pervious, and then the impervious is going to be its relative area times the curve number of the impervious. So this table combines all this together. It's saying the impervious, let's assume about 100 for the impervious curve number. And so we have to define these three other things. We have to define the relative areas of the pervious and the impervious, and then also the curve number of the pervious. And so the area thing is defined by, we're saying it's a mix of either pervious and impervious. And so the 30% is when we say how much of each we've got. And then these pervious curves is where we define what is the curve number of the part that isn't asphalt. So this table is essentially just a weighted average. There's nothing special going on in this one, but in this one, it is kind of special because think about the runoff from this asphalt is not going straight to the outlet. Before it gets to the outlet, it's going to flow through this portion of the watershed that allows for infiltration. And so the rain that falls on the pervious surface, a portion of that is going to be infiltrated. But even the rain that fell on the impervious area, it has a potential for some infiltration as it flows over the pervious area. So whereas we calculated a curve number of 72 if we had 3 acres of pavement that was directly connected, if that same area, if the same 3 acres is up top, we'll go through the process, but what we're going to see is that the curve number is lower because some of the runoff ends up infiltrating as the water flows over the pervious area. So the way that we go through this is, first of all, we have to start with the ratio of unconnected to the total impervious. And so this impervious surface right now is completely unconnected to the outlet. It's not directly connected. Like it was here, it was directly connected. So over here on the vertical axis on the right, we have 100% of the impervious is unconnected. So you'll see here this ratio where it says unconnected impervious to total impervious. So we have 3 acres of impervious surface, and all of it is unconnected. So we're going to use this 1.0 curve. And then the total for the entire watershed, 3 out of 10 is impervious, and so 30%. So we go over at the intersection of 30% and 1.0. We start moving to the left until we reach the curve number that represents our pervious, our pervious surface, the grass curve number of 60. So we're going over here until it intersects with this right here, the curve number of our grassy area, and then we bring it down to the intercept on the horizontal axis, and it's in the range of 65. So again, let's just go sideways over until we reach 60, and then down. So between 60 and 70. So the effect that this is trying to account for is the fact that the sheet flow that's coming off of this parking lot, that sheet flow, some of the water will get into the soil as it flows over the grass. Not all of it, but certainly more than in this case, because in this case, all of the sheet flow from the parking lot just went straight to the catch basin. It's the same idea when we said that it's a best management practice for people to disconnect their roof drain from a combined sewer. You know, here in Huntington, some people have the drain from their roof going into the sewer. And then when it rains really hard, that kind of contributes to the risk of there being sewage discharge into Four-Pole Creek and Ritter Park. But if people disconnect their roof drains, then that means that the water has to flow over their front yard before it gets into the catch basin. So it kind of reduces the amount of rainfall that ends up stressing out the combined sewer. So this is a similar effect. In this case, we had 100% of it was unconnected. Just to round out the example with one more look, now we have some of the asphalt is directly connected. Some of the asphalt is unconnected. So it's half and half. And that's where on this right curve where it's saying the ratio of unconnected to total for the impervious. So we have 3 acres of total impervious area, and 1.5 of it is unconnected. So that means 1.5 divided by 3, this 0.5 curve is what we would use. And our total impervious area is 30% because it's still 3 acres out of 10. So we're using this 0.5 curve and 30%. So we go over until it intercepts the 60, which is the curve number of our pervious area. And then we take it down from there to the intersection of the horizontal axis. So the curve number effectively would be 68 for this. So it's kind of a mix of direct connected and disconnected impervious area. Now I think I've said impervious enough times for the day. Any questions about this concept? All right. That's all we've got for today. So with the composite curve number and antecedent moisture conditions, I think that rounds out all of the topics that are accounted for in the homework assignment. But if you have any questions, feel free to send me a message or stop by my office hours. Have a good day.